Everyone in the back? All right. Hello, everyone. My name is Nikhil Pimpalkhare. I'm coming from Princeton University, and I'm going to be presenting my work with Zachary Kincaid. The title of this talk is also an outline of this talk. And so what I'm going to be talking about today is what problem I solve, monotone procedure summarization, and then I'm going to talk about how I solve it with vector addition systems and inductive potentials. Here is a summary of what I'm about to say. Existing verification techniques are based on heuristics and can behave counterintuitively. And so let's build new ones, formally guaranteeing predictability. So probably all of you are familiar with the program verification setting, where you have a program like this one. The details aren't important. And you have a specification like this one, which says that this add function actually computes the addition of its inputs. We have some state-of-the-art verifiers like Korn and Ultimate Atomizer that, given these two, say, yes, this program meets this specification. These two tools are model checkers. And what model checkers often do, given a program, is that they compute an over-approximate summary of what each procedure's semantics, and they use this summary in order to interpret procedure calls. And then they do a counterexample guided loop in order to prove or refute a property about the program. But this is not a talk about model checking. This is a talk about procedure summarization. So I only care about this component, the process of computing an over-approximate summary of each procedure's semantics. I'll comment that procedure summarization has clients beyond program verification, but in this talk, I'll only be talking about verification. All right, so we have a software verification competition, and according to this competition, these are the best verifiers to use when you have a recursive program. But these tools display some counterintuitive behavior on related queries. So they both succeed in showing that this program meets this specification, but what if we considered a different specification? So this specification says that the add function is increasing in the second input. A question. Which specification should be easier to prove about this program? One answer for that is that the blue one should be easier, because the red property implied the blue property. The red property is a stronger description of program semantics, and so it should be harder to prove for this program. Well, unfortunately, Korn and Ultimate Atomizer don't agree with this intuition. They succeed in proving the red specification for this program, but they fail to produce an answer when given this blue specification. And so they behave a little bit counterintuitively on related specifications, and they also behave counterintuitively on related programs. Consider these programs. These programs are both recursive programs, and they only differ in the conditional guarding the base case. The red program on the left has a non-deterministic guard. So every time the conditional is hit, it arbitrarily chooses true or false. And the blue program has an n less than or equal to 1. So a question, which program should it be easier to prove specifications about, the red program or the blue program? One answer is that the blue program should be easier, because it's a refinement of the red. Every execution of the blue program is an execution of the red program. And so if I prove something about the red program, then I'm proving it about more executions. Proving it about more executions should be harder. But again, Korn and Atomizer do not agree with this intuition. So the core reason for this unpredictability is that the state-of-the-art in procedure summarization is driven by heuristics. And so it's difficult to predict how the procedure summarizer is going to work on related queries, because they may interact with these heuristics differently. So the goal of my work is to develop a predictable procedure summarizer in the sense that it is compositional and monotone. A compositional procedure summarizer will compute the summary of a procedure from the combination of its parts, and will allow us to reason about the effectiveness of the summarization technique on composite programs. And a monotone procedure summarizer will compute at least as strong of a procedure summary for a refinement of a program as for the program itself. And so this will give us a way to reason about the effectiveness of the technique on related programs. For the rest of the talk, I'm going to show you my monotone procedure summarization technique working on this verification task. This verification task involves an integer model of a program which accesses memory. And I'm trying to bound the number of times that it accesses memory. Imagine a program that traverses a binary tree. And at each node, it saves the value of the node to a buffer. And at each leaf, it writes everything in its buffer to memory and clears out the buffer. This program is an integer model of such a program in which size represents the size of the binary tree, buff represents the length of the buffer, and writes counts the number of times that we write to memory. So at every node, we increase the length of buff because we need to add the current node into our buffer. And at every leaf, we make buff writes, and then we reset the length of our buffer to be 0. I'm going to show you how I compute a procedure summary of this procedure in a monotone way that is strong enough to show that the number of writes that this program makes is bounded by the size of the tree. So a rational vector addition system with resets is just a program in which all of the variable assignments are of a particular form. And so I'm going to compute procedure summaries in a monotone way by computing the best VASR abstraction of a program and precisely computing its dynamics. So first, I'll formalize what I mean when I say best abstraction. Given a program, I want to compute a VASR program and a simulation function f, such that for every pair of states which transition to each other along the program, the image of these states under the simulation function f transition to each other in the VASR program. In prior work, Silverman and Kincaid computed the VASR abstraction of the body of a while loop. And then they computed the set of states that this VASR could reach over an arbitrary number of transitions. And then they took the inverse image of this set under the simulation function f, and they got an over-approximation of the set of states that the while loop could reach over an arbitrary number of iterations. In other words, a loop invariant. Now, what I am doing is that I'm computing a VASR abstraction of the body of a procedure. And then I'm computing the reachable set of states of this VASR along transition sequences corresponding to the recursive structure of the procedure. The language L of such transition sequences is a context-free language. And so I'm going to be computing the context-free language reachability of VASR. Then, like before, I take the inverse image of this set under the simulation function f, and I end up with an over-approximation of the set of reachable program states along arbitrary executions of the procedure. In other words, a procedure summary. Now, I don't compute any VASR abstraction. I compute the best one, which is called the VASR reflection. The VASR reflection of a program has the property that for any other VASR abstraction of the program, there exists a simulation from the VASR reflection to the other VASR abstraction. Simulation can be thought of as a loss of precision. And so the VASR reflection is going to lose some precision compared to the program, but any other VASR abstraction is going to lose precision compared to the VASR reflection. So the VASR reflection is best because it captures as much about program semantics as any VASR abstraction. I keep saying VASR. What is a VASR? A VASR is a program in which all of the variable assignments are of the form variable equals constant or variable equals variable plus constant. And I'm going to be computing VASR abstractions which linearly simulate the program. This means that the f function on the previous slide is going to be a linear function. And in simple terms, this means that the variables of the VASR represent linear combinations of variables of the program. And so my first contribution is an algorithm to compute the VASR reflection of a program, which linearly simulates any other VASR abstraction and is therefore best because it captures the most about program semantics of any VASR abstraction. So here is our running example. And here is its VASR reflection. The VASR reflection has two variables, A and B. A represents buff, and B represents buff plus writes. The program assignment buff plus equals 1 gets translated to A equals A plus 1, and B equals B plus 1. And the combination of commands writes plus equals buff and buff equals 0 gets translated to A equals 0 and B equals B, because the new value of writes gets the old value of writes plus the old value of buff, and the new value of buff is 0, and so the term buff plus writes remains constant. The key contribution of my work is that we can compute the CFL reachability of VASR. So for this VASR, we can conclude that after any execution, we know that the A variable is going to be 0, and the B variable is going to be some non-negative k, where k represents the number of times that the tree count function is symbolically recursively called. I'll say a few comments on this contribution for the experts in the room. The way that we did this is that we compute the Peric image of an expanded version of the grammar of the context-free language. And this object contains enough information to compute the possible net effects of the VASR along any transition sequence inside of the language. So given our exact summary of how the VASR works, we replace the A's with buff and the B's with buff plus writes, and we have an over-approximate summary of the semantics of the program. Now, I've presented everything here in terms of VASR, but this also works in terms of lossy VASR, which is a relaxation of VASR to inequalities. Lossy VASR is better than VASR because every VASR assignment can be viewed as a less than or equal to and a greater than or equal to. And the lossy VASR can abstract additional information about the program, like the fact that x is less than or equal to 0, that the VASR cannot. All right, so using VASR-based summarization, we were able to compute an over-approximate summary of the semantics of this program. But this over-approximate summary is not yet strong enough to prove the property that we wanted to. The core reason for this is that the VASR is losing information about the maximum number of times that the tree count function can be recursively called as a function of the input. And so the way that we're going to refine this summary is that we're going to synthesize bounds on the number of times tree count can be recursively called, and we're going to apply them to this k variable. And in doing so, we're going to strengthen the summary enough to be able to prove this property. We synthesize these bounds with inductive potentials. So we compute a refined summary in a monotone way by computing a potentially infinite set of bounds on recursive call count and applying all of them to our summary. So we search for bounds on recursive call count of this form, where the x's are program variables and the a's are constant coefficients. In order to synthesize and apply bounds in a monotone way, at a high level, we compute a polyhedra, pictured here, such that every point in this polyhedra is an assignment to the a coefficients that would be a bound on recursive depth for all possible inputs. And then we use polyhedral techniques in order to finitely encode the bounds associated with all points in this polyhedra into our summary formula. When we apply this refinement to our previous summary, we now see that k is bounded to be less than this term. And our overall summary is now strong enough to prove the property that we wanted it to. All right, so I implemented this technique and we evaluated it on the recursive category of the software verification competition. But this benchmark has some weaknesses as a evaluation setting for procedure summarizer. One issue is that it contains a lot of programs which are difficult for procedure summarization, like the Fibonacci function or the Ackermann function, but checks properties about them that can be checked via execution, like checking that the Fibonacci of 7 is equal to 13. Another problem is that there are many copies of tasks that involve the identity function, the Fibonacci function, and the addition function, and so there's low task diversity. And so our final contribution is a benchmark of diverse recursive programs, and none of these tasks can be solved via execution. Here are the results of our evaluation. Recursive and recursive simple are the recursive category within SVComp, and our new benchmark task is called Rec Supreme. On the left-hand side, the red tools are procedure summarizers, the blue tools are model checkers, and the tools labeled M are guaranteed to be monotone. From this evaluation, we can conclude that our tool, LIP, represents a step forward in procedure summarization, and that in some settings, it is even competitive with model checkers. When you have two techniques for monotone procedure summarization, you can use them both on the same procedure and then conjoin the resulting summaries, and the overall aggregate procedure summarizer is also guaranteed to be monotone. So we did this with LIP and compositional recurrence analysis, and their aggregate procedure summarizer is also guaranteed to be monotone, and it's strong enough to solve some tasks that neither one of these tools can solve individually. So thank you all for listening to my talk. Today you heard about a new technique for procedure summarization, which is predictable by being compositional and monotone. Here are the key technical contributions of my work, and thank you again.
Okay, we have time for questions. Just step up to the microphone.
Thank you so much for the talk. So I just wanted to get a better sense of what kind of properties can be improved using this abstraction. So like when you get the best VASR abstraction, what kind of properties are you checking against it? Like, can it have like quantifiers or?
So the property that you want to check about the overall flow of these procedure summarizers in verification is that you compute the summary and then you check if the summary implies a particular value. And so I don't know off the top of the head what the quantifier situation is in the properties that we checked, but if the procedure summary is strong enough to imply that property, then you would be able to prove it with this technique.
I see. And then to check that the abstraction satisfies the property, like do you use like some SMT solvers, or is it like?
Yes, we make a query to Z3.
Okay, gotcha. Thank you.
Hi, thanks for the talk. This was presented well enough for me to ask a question. So your motivation was predictability, but I couldn't quite tell how you were actually evaluating whether your end result was more predictable than previous tools. How exactly are you evaluating that element of it?
In terms of predictability, by formally guaranteeing this monotonicity property, we argue that in practice it's going to be more predictable than other tools. And then also in this Rec Supreme benchmark set, we have a couple of, for each program, there's a couple of different specifications that we try, usually of decreasing strength. And so UAutomizer and Korn have this thing where sometimes they fail to prove a weaker specification, and our monotonicity guarantee allows us to solve all of them.
Got it. So in this context, anything that's monotone is predictable for the context of this?
Yes.
Gotcha. So I guess the other competing tools, like the CRA or I guess it's only CRA, right? Because you're combining it with LIP. Like that one is also predictable.
Yes, that one is also predictable in this way.
Okay, thanks.
Hi, thank you for the nice talk. So my question is, the two motivating examples that you've had, it seems to me that the difference between the programs and specs that Korn and UOptimizer can prove versus not is that there exists some conditional branching that they could not handle, which I assume is very nicely handled by VASR because this is abstracted as non-determinism. So are the examples that you're able to solve and UOptimizer and Korn fail on mainly these examples where some problematic conditional branchings are abstracted? Are there also some other examples that basically you could handle and they could not?
So I think the paper is the best place to look for the examples where we succeed and Korn and UOptimizer fail. But I think that there are cases in which, in particular when we're using lossy VASR, where we are able to abstract the conditional. And even with that, we still are able to prove.
So you get another conditional and still, am I understanding this correctly?
We are still able to abstract information from the conditional.
All right. Maybe I'll look at the paper. Thanks.
Let's thank Nikhil again.